Hi folks, this is BGP lecture number 2. Here I'll cover a few BGP basics. So as we said before, BGP is a path vector routing protocol as defined by RFC 4271. It's also called an advanced distance vector protocol, and it is a distance vector protocol because it's really relying on its neighbors to pass along routes from one peer to the next. And that's how it gets the routes into the routing table. The BGP route carries data with it that lists the AS numbers that must be traversed to reach the associated destination network. Much more on this later. So the role of BGP really is, of course, to exchange routing information between autonomous systems, but it also must guarantee that the routes it passes along are loop-free. Now BGP 4 is the current version of BGP, and it supports CIDR and route aggregation. Now whereas common IGPs such as RIP, OSPF, and EIGRP use technical metrics to assess the desirability of the route through, let's say, a smaller number, whether it's hop count in RIP or cost in OSPF, EIGRP. BGP does not do this. It does not use technical metrics. There is a metric keyword in BGP, but you'll see later that it's really got nothing to do with the metric of the route itself. BGP makes its routing decisions based on an algorithm and on network policies. BGP does not show the details of the topology within each AS. It simply sees a tree of these ASs, and each route then will show you, as I said before, which ASs must be hopped through in order to get to the destination. The paths that are held in BGP on each router can be seen on a Cisco router with the show IP BGP command, and we'll look at that much closer later on. So BGP relies on TCP, and it uses TCP port 179. Now in contrast, RIP updates use UDP on port 520, and OSPF, IGRP do not use a layer 4 protocol at all. Do you remember, I don't know if you remember what EIGRP does, but it uses reliable transport protocol, so there's no IP transport protocol at all, nothing at layer 4. Now because BGP rides on TCP, only IP connectivity is necessary between BGP peers. Unlike the other routing protocols we've looked at up till now, which have to be directly connected, right? Peers are directly connected. Now, that's being said, for external BGP sessions, if they are not directly connected, then there is some extra configuration that is required to account for that. More on that later. So TCP is used, and therefore standard TCP connection has to be negotiated before peering is going to be established. But because of that, we don't really need to do anything else to get reliable communications, because BGP inherits everything from TCP, so it's connection oriented and reliable. So speaking of loop-free paths, as I said, each BGP route carries a list of AS numbers called the AS path. And this is actually constructed as the route is advertised between external BGP neighbors from one AS to the other. And this AS path is considered what we call an attribute of the BGP route. We'll look at more attributes of BGP later on. So as this network reachability is advertised and passed along from one BGP speaker to an external BGP peer, its local AS number is going to be added to this AS path, and that's how it gets built all along the way. Any BGP route that represents reachability then to a given destination can be then examined to see the AS path, to see the order in which the ASs have to be traversed to reach that destination. So to guarantee this loop-free path, then any route received from a peer will be discarded if its AS path already contains our local AS number, because that means we've already seen this route and we already added our AS number to this path, and now we're seeing it for the second time. So here's a more detailed example. If we now consider the routes from AS7, which is at the very top here, consider the routes from AS7 to reach destination 172.16.00/16 down in the bottom right at AS1. Okay, so we're going to look at the BGP route advertisements from AS1 upwards. So remember, the AS path, which is what we've listed here, if I come up this way, up from AS1 to AS2 to 4 to AS7, then the path, AS path, will contain 4, 2, 1, because the reverse order is put into that path such that when you read it from left to right, you can see that now it is following that path. Compared to seeing this path advertised to the left here through AS3, AS5, AS6, then by the time we reach AS7, this path will have 4 ASs. Okay, so the shortest inter-AS path is imputed to be the one that contains the least number of AS numbers in it. And all things being equal, BGP will prefer the routes with the shorter AS paths. Again, later we'll look in detail at what the algorithm is that helps BGP determine which path to use first. So given that in this example, AS7 then would choose the shorter path to the right down through AS4, AS2 to AS1 to the destination. And yes, later we'll talk about what happens if we do have equal length AS paths. Now in terms of loop avoidance then, in this example, let's look at what happens with that same path as it's advertised up from AS1 through AS2, AS4, and it reaches AS7. Let's suppose that we have another AS8 and 9 added to our topology here, our picture here. Then as that gets advertised up from 7 to 8, that same route, then the AS7, as it leaves AS7, is going to prepend the 7 onto the AS path. So you can see now the AS path as it sits in AS8 is going to be 7, 4, 2, 1. Right? 7, 4, 2, 1, which is exactly what you expect. As that same path is advertised to AS9, then AS8 will prepend its AS number to the front. And then, as that path gets re-advertised back to 7, let's say because AS9 is also connected to 7, well, AS7 will see that its AS number is already in the path, and therefore it will reject that update. It will discard that update. And that is how BGP avoids looping, paths that loop through the AS more than once. Here's another example. So let's say we start off at AS 500 here, and AS 500 advertises a path to some destination, we're not saying where in this case, to AS 100. So when that first advertisement happens, the AS path with that route will be 500. Then, as AS 100 advertises upwards to AS 200, it adds its paths, prepends its AS number to the path, sorry. And so now you can see the path is 100, 500. In the next iteration then, as AS 200 advertises AS 300, then 200 gets added to the front of that path. And in the fourth iteration, 300 gets added to the front. And next, as AS 400 advertises to back to 100, it prepends its path on there. But then AS 100 sees that its own AS number is in the AS path, and at that point AS 100 will discard that route advertisement coming from this direction.